So today we have a really, really great presentation for you from a team of engineers from the Lab Center for Advanced Materials and Engineering. And without further ado, let's bring out the team. Melody, Will, Eric, Julie, and Chris, and I'll let them say a few words.
Hi, my name is Melody, and I am a materials engineer at Lawrence Livermore National Lab.
My name is Julie, and I'm a mechanical engineer.
Hello, I'm Eric Dewis, and I am a materials engineer.
Hi, I'm William Smith. I'm a mechanical engineer at the lab.
And I'm Chris Spadaccini. I'm an aerospace engineer at the laboratory.
And joining them today from Tracy High School Science Department, Dean Reese.
Hi, Dean, buddy.
Okay, so these guys and gals have a lot to tell you, so let's get on with the presentation.
So I am guessing that most of you are here because you've heard about 3D printing and you've heard about how it has the potential to revolutionize our world. So we are here to take you through the wonderful world of 3D printing and show you how at LLNL we create materials that have unique properties that have never before been observed. But before we get into all that, we're going to give you a little background on materials and give you an idea of how 3D printing fits into our modern world. So materials are all around us. We interact with them on a daily basis, but maybe don't realize that, or maybe don't think about that. And so if you take this house for an example, there is a variety of materials we see here. There's the bricks, the shutters, the glass, the insulation in the walls, the carpet, the tiles. So all of these different types of materials have their own purpose and are made in different ways. Materials are used either in their raw form or as an input to a manufacturing process. For instance, if you take a look at these solar panels, they are made from carefully constructed materials that absorb the sun's energy in order to create electricity. So the way that they are made is directly tied to their application. Another way in which material science and manufacturing technology affects our daily lives is through our communication devices. In a time where being connected is so important, we rely upon our laptops and smartphones to keep us in the loop of what's going on in the world. So while you look at these devices that you're so familiar with, I want you to stop and ask yourself a couple questions. How does the screen on your iPad respond to touch only when and where you want it to? How does the screen display color or the details of your Snapchat? These questions are all part of a larger theme that we're going to discuss today, and it is how are materials made and how can 3D printing be used to make them better? So, back in the day, before the first industrial revolution, pre-1800s, things were really hard to make because everything was made by hand and it was often slow, tedious, and dangerous. There were a few number of skilled craftsmen in charge of making tools and other things we would use, and they would put in a lot of effort in order to get a very small amount of output. And so this affected daily lives significantly because you didn't have access to the tools that would make your jobs and your lives easier. And so if you think about the phrase, work smarter, not harder, that's not happening here at all. So with the advent of the first industrial revolution in the beginning of the 1800s, we see a huge increase in our ability to manufacture things. And this is partly due to our adoption of the factory system and our use of machinery in these factories. So we start to move away from this idea of small number of skilled craftsmen to having a division of labor and make things more efficient and have a higher output. And so because of this, this was a time of incredible innovation that we had never before witnessed. Once we get to the second industrial revolution, we continue to develop these ideas through of increased output and efficiency using the assembly line, and we continue to develop the machinery that we're using and the way that we power this machinery. This time was also known as the technological revolution because science and engineering played such a huge part in our advancement. To give you an example, the electrification of factories has been known as the most important engineering advancement in the 20th century by the National Academy of Engineering. So that gives you kind of some context of the type of innovation that was happening at this time. Furthermore, the use of railroads, telegraph lines, and ultimately telephones meant that people, and more importantly their ideas, could move freely throughout society. Additionally, we had a lot of interest in developing materials like iron and steel, and in creating new materials such as alloys. At this time, material science and chemistry became a more developed science that we continue to use today. So because of all of this development we had during this time, we now have automobiles, we have electricity in our homes, we have steel to make skyscrapers, and we have telephones in our homes and also our pockets. So some people say that now we are on the cusp of the third industrial revolution, and 3D printing is the key to that idea. So the way the manufacturing process would look here is that you create a design on a computer, you then build that design using a 3D printer, and voila, out pops this custom fabricated part with all of the complexity that you may want or need. This also means that anybody with a computer can be contributing to the advancement of technology. So this distance between your imagination and the realization of your ideas is getting smaller and smaller, and that is really exciting. So now, hopefully, you understand why people are so amped up about 3D printing. 3D printers are becoming very commonly available, and they're being used to print everything from cars to clothing and computer parts. So at this point, you may be wondering, how do 3D printers even work? And so I'm going to have Julie come out and explain to you exactly what's going on.
Okay, thank you, Melody. So before we dive too deep into how 3D printing works, let's actually define what 3D means. 3D means three-dimensional, and this can be described with the Cartesian coordinate system on screen. Now, most of you have probably seen this in your math or physics courses, but for those of you that aren't familiar with it, what the Cartesian system does is it defines an x, y, and z dimension for all 3D objects. So take me, for example. My width is my x, my depth is my y, and my height is my z. So why is 3D printing or additive manufacturing sometimes better than traditional or subtractive manufacturing? On screen, you're going to see a video of something called a lathe. What a lathe does is it has to carve away material to create your 3D part. Now, this can be extremely hard to make really complex features, especially in the inner volume of that dowel. Additive manufacturing, on the other hand, or 3D printing, only puts material where you want it. And in this way, it's actually very easy for us to make complex parts. It takes just as long to make this bowl with holes in it as it would a solid bowl. So because of the way that these processes work, 3D printing actually minimizes waste. So we have subtractive manufacturing at the top, and you start with a solid chunk of material, say metal, wood, plastic, and you have to carve away that material to get your structure. You're left with a lot of waste, like you saw in the first video, all those chips flying off the screen. 3D printing starts with a raw material, say powder, a plastic filament, whatever you can use, and it places that material only where you want it. And in this way, when you have your 3D structure, you're left with little or no waste. So we actually have a 3D printer here on stage, and I'm going to bring out Dean to talk to you about it.
Thank you, Julie. All right. So one of the first things you'll notice here is there's a computer that's hooked up through a USB cable to the 3D printer. And on the computer, there's a CAD file, computer-aided design file that someone designed. And it's actually of, in this case, we're 3D printing a unicorn head, which is kind of cool. And so that design is fed in, and really that file has information for every layer of this object, right? So if you look closely at this, and it's going to be hard for you to see from there, but there are tiny layer after layer after layer, smaller than a millimeter in size, that just get laid on top of each other to form this object. And so there's a spool back here, and that spool has plastic, like a wire of plastic, and that's called filament. And that comes up to the top of the machine here, down into an extruder. And that extruder's job is to heat up the plastic and melt it into a liquid so that it can get pushed out of a nozzle. And then, just like Julie was telling you, we really have to worry about the X, Y, and Z axes, right? So the Z axis, which is the vertical axis, is being kind of controlled by this print bed that's moving up or moving down to basically allow the object to build. And then the extruder is on these motors that can move in the X and the Y, and which is basically allowing it to precisely lay plastic down to build layer by layer the object that you have fed into the machine through the computer file. Okay?
All right, thank you, Dean. Okay, so one of the really amazing things about 3D printing, and Melody alluded to this, is that you can turn your ideas into 3D objects in a very short amount of time. So every day, people in our lab come up with these crazy ideas, and we draw them up in something called computer-aided design, or CAD for short, software. Now, once we draw up these 3D models, we export that CAD file into our 3D printer, and out pops our part. Now, it's not quite that simple, but those are the basics. Now, every once in a while, when you get your structure, your final part, you realize that you want to make some changes. And so you have to go back to your CAD design, make some tweaks, and then reprint. This is what's known as the design iteration process. And this is a common process that scientists and engineers do when they're designing something. Now, 3D printing, because it's so quick and easy to build your structures, drastically shortens the amount of time for that design iteration process. So 3D printing opens up a world of new designs. Designs that were once impossible are now possible. We have a set of just an example on the screen. I know you guys are probably thinking, number one is not new. That's the Eiffel Tower. That was built in the late 1800s. But the thing about the designs on screen is that they were all built in one shot, so one piece. Another cool thing is that you can actually build functioning parts. So design number 4, that's a planetary gear. And right off the build plate, that gear spins and moves. So now that you guys are all experts in 3D printing, I'm going to bring out Eric to talk to you about what LLNL does in 3D printing and why we like to come to work.
Great. Thank you, Julie. Yeah, so what do we do at Lawrence Livermore with 3D printing or additive manufacturing? Well, we get to innovate. That is, we get to dream of new things and create new technologies for 3D printing. But the way we look and approach 3D printing is in a very holistic fashion. That is, it's not just about the process itself. There are other aspects of it that you have to consider. For example, feedstock materials. You have to know what is being input into your process to derive better outputs. Of course, we work on the processes themselves, and we do this by advancing and expanding upon existing 3D printing technologies, but actually creating entirely new 3D printing processes that you won't find in commercial industry, and in fact, you won't find outside of Lawrence Livermore. Modeling and simulation, that is, can we use our supercomputing capability? We often have some of the largest computers in the world, fastest computers in the world, most powerful computers in the world, to really understand the physics that underpin these 3D printing technologies. And of course, how can you really take advantage of this very exquisite, complex design space that is made possible with 3D printing? How can you convince designers and architects and engineers to think about manufacturing in a new light? And lastly, applications. I think this is what really gets us as scientists and engineers really excited about this technology, is that each and every day we get to learn new things because the technology is very enabling. It allows you to approach things in new technologies in new ways. and explore structural mechanical materials, things for aerospace and transportation, but also functional materials and properties. Things like, can you make electrically conductive materials? Can you make things that are magnetic or have really interesting optical properties? This is a new space that I think folks in 3D printing are really starting to explore now. Okay, so what do I mean by feedstock? Feedstock is literally the stock from which, or the stuff from which you feed into your printer. So there's a well-known phrase in computer science, garbage in, garbage out, okay? You know this from the food that you eat every day. You need to eat nutritious and nutritious foods that allow you to grow, allow you to provide you the energy to perform, and really advance yourself. So it's important for 3D printing as well. So what we show here is actually a thermoplastic filament material that is commonly used for the 3D printing technology that we have here on the stage that Dean introduced. It's a material, thermoplastic, that can be melted in a heated print head. And once it exits that nozzle, it'll solidify because it cools, as opposed to a thermoset. A thermoset is a material that is highly chemically cross-linked and will actually, in fact, not melt. Okay, so what we have here on the stage and what we do at Lawrence Livermore is actually create customized functional feedstocks. And we can make them from, for example, nanoparticles. So what we have showing on the screen here now is nanoparticle suspensions, where you'll notice there are different colors that span the gamut of the colorimetric rainbow. And the reason they're colored is not only because we're changing the chemistry, we're also changing the size and the shape and the concentration of these nanoparticles. And you can actually see that with these particular suspensions. So what is a nanoparticle? You won't realize it, but if you really were to zoom in on this and magnify it, they have discrete particles that are making up that color. And nano refers to a nanometer. That is a unit of length that's very, very small. In fact, you can think about it this way. Take a hair from your head, split it lengthwise, split it in half. But do that 10,000 times. So you have 10,000 pieces that would have made up that strand of hair. Each one of those strands would now have a diameter on the order of a nanometer. So very, very small. In fact, you need an electron microscope to actually even see these particles. Okay, so if we go back to the slides. All right. So here's a photograph, an optical photograph of something similar to what we at Lawrence Livermore made here with those nanoparticle suspensions. But on the bottom, you see electron micrographs, and I mentioned we can change the size and the shape with chemistry. That's really extraordinary control now, where we have pyramidal structures, we have cubic structures, we have wire-like materials. What we can do is we can take these and actually formulate them into an ink or a resin and use them as a feedstock now for our 3D printing processes. This is just one example. We work with many, many different types of feedstock materials, including some that are, for example, flexible and stretchable, some that, as I mentioned, can be electrically conductive. Okay, so our feedstock materials can be derived from many different material classes. And by material classes, we mean things like metals, ceramics or glasses, or polymers. And there's actually a field of study of materials called material science and engineering. I encourage you to look at it and actually consider it for a career. So as you're well aware, these materials, these broad material classes have very different properties. Metals can be highly electrically conductive, thermally conductive, they're mechanically strong, and in some cases, though, in the case of a can here, when you deform it, it'll tend to deform permanently. They're ductile. Glasses have interesting optical properties. Ceramics can have interesting optical properties. They have good thermal resistance. They're thermal insulators. They have good chemical resistance, and it can be used for a variety of applications. However, when you impact them, they tend to fracture. They're brittle. We'll have a demonstration of this in just a second. And then polymers. Polymers are ubiquitous. They're lightweight. They're inexpensive. They're easily formed and manufactured. And they have a wide range of mechanical properties that you can achieve. And we'll give you a little demo here in just a second. So I'm going to bring out Will and Dean to the stage.
Thank you, Eric. So As Eric just mentioned, we have 3 material classes that I'm about to demonstrate for you today, and particularly I'm going to be testing their impact strength. So representing the metals, I have this metal Coke can, and glass or ceramics, I have a light bulb here in the bag, and I also have this plastic bottle representing the plastic polymers. I'm going to hit each of them with a hammer, and we're going to see how they react. So you have the can, hit it with the hammer, you see that it deforms permanently, but it still remains intact because it is a ductile material. Now the light bulb, on the other hand, when you hit that one, it fractures, and you see there's no way you're going to ever be able to put this back together again. Now the plastic, on the other hand, even though he did mention that it's weaker, when you hit this with a hammer, it deforms, but it's able to regain its shape because it's a lot tougher material. So this just goes to show that we have 3 different material classes, and they have different material properties. You need to keep this in mind when you're choosing your material for manufacture.
Thank you, Will. Okay, so that was our crush demonstration, just to illustrate different material classes. Now, what do we do with these feedstock materials? We take them and we put them into some of our 3D printing processes. So we develop these often with academic collaborators. The first process I'll tell you about is called projection microstereolithography. It's a mouthful. I encourage you to try to say it 3 times fast. And what is this technique? It's a photochemical technique, okay? Where we start with a computer-aided design model. That is a computational model of a complex geometry, such as this unit cell shown here. We discretize it. We slice it into layers. And then we project that using a spatial light modulator, akin to what we'd find in the projection system in this theater today. And we focus that image through some optics onto the free surface of this liquid resin. This liquid resin has really interesting chemistry to it. That is, wherever it's exposed with light, it'll change its phase from a liquid to a solid. It's a photopolymer, okay? And what we can do is we can change that image on the fly, and as we lower that part into the resin bath, we can grow that 3-dimensional geometry or part, literally from a pool of resin. I think that's really cool. A second technique that we work on is something called direct ink writing. So this is very similar to the fused deposition modeling approach that Dean showed us here today, except for we replace that heated print head now with a print head that can extrude inks at room temperature. But these inks are carefully designed in terms of their flow properties. That is what we call their rheological properties, so that they're shear thinning. As they're being sheared in the nozzle, they'll lower their viscosity or their resistance to flow. However, once they exit the nozzle, they'll rapidly set and maintain their shape, such that you can print up structures in a layer-by-layer fashion. Also, what's really interesting with this approach is you can deterministically deposit onto not only planar substrates like you see in most 3D printing processes, but actually non-planar 3-dimensional objects. Now, the 2 techniques I just showed you either expose a 2-dimensional image of light and do that in a layer-wise fashion, or raster a point source to build up the part. Wouldn't it be cool if you could actually, in a single shot, form a 3-dimensional geometry? And that's what we have. Lawrence Livermore invented a new 3D printing technology called holographic 3D printing. So what we do is we define a 3-dimensional pattern of light. We have one of these photopolymeric resins. And if you create that 3-dimensional light image in that resin, now in a single shot, in a matter of seconds, you can create a 3-dimensional object. And as we drain the resin, you'll see, in this case, it's a simple object, a cubic-like architecture, but it's done in a single shot. So that's something that we invented at Lawrence Livermore. Okay, in addition to working with polymers, you can work with metals. There's a process called selective laser melting. The way this works is you have a metal powder bed, and you raster a high-power laser across the surface. Wherever that laser hits the metal powder bed, it'll locally fuse and melt or sinter that powder together. Wherever it's not exposed to, it will stay free-flowing powder. So what you do is you shoot a layer, and then you roll out with like a squeegee or a roller another layer of powder, and you pattern the next layer. And you do that again in a layer-wise fashion. And you can actually make objects out of metals and metal alloys. Aerospace industry is very interested in this technology. And it's very important for us to understand the physics that really underpin these processes. And we often do that with high-performance computing or supercomputing at Lawrence Livermore. So what I show here is actually a computational simulation of this selective laser melting process, where with the computer now, we're rastering that laser across a metal powder bed surface. You can see the red region is where the laser front is, and we can see how the metal powder is melted, how it's deforming, how it's changing in terms of its temperature, and so forth. The reason this is important is because microstructural behavior and effects will really determine the macroscopic types of properties that you observe in terms of mechanical performance and so forth. So this really allows us to understand the physics of the process and really start to think about improving the process by changing the process conditions or the material conditions. Okay, we also use supercomputing or cloud computing or even your computer at home to design for additive manufacturing and 3D printing. And that's what we're going to tell you about next. I'm going to welcome Will out here.
All right, thank you, Eric. Now, as Eric just alluded to, we often use computers to help us in aiding us into the optimization of the design of our materials. And this next video I'm going to show you is from our partners at Autodesk, and it's going to give you a really succinct overview of how that process is carried out and the possibilities that lie within it.
What if you could come up with thousands of options for a single design without drawing, all of which meet specific goals set by the designer? And from those options, pick the one design that delivers on the most important criteria, the design you couldn't possibly have imagined. This is generative design, a technology that harnesses massive computing power, creating forms with precise amounts of material only when needed, achieving maximum performance while wasting nothing.
Now, in that video, you may have noticed that for the design of that drone, there were a lot of really funky looking designs that you wouldn't intuitively come up with. And this is just one of the advantages of having a computer aid you in your design process. And as he said, you can, with this type of process, you can have material only where you need it, because given your application, you might not need material in some other places, and it'll depend on what kind of load your material is going to be carrying. And we keep this mindset in mind when we are designing our structures, our architectures. And when I say architecture, what I mean is instead of having a bulk solid chunk of material, you instead infill that volume with a lattice of beams that interconnect in a really complex way to make your material a lot lighter, but still maintaining the same relatively higher stiffness. And one good way to understand this is to draw a comparison between the pyramids in Egypt and the Eiffel Tower. Now, the Eiffel Tower, it is twice as tall as the pyramids, yet it's almost 1,000 times lighter. And the reason for this is pretty obvious, because you can see that instead of just a giant pyramid of metal, it is made out of a lot of little beams that are connected, and there's a lot of airspace in there. And you can imagine that this type of design would allow you to build this type of structure a lot faster. And so when we're making our materials in the lab, when we're coming up with our lattices, we need to know where our lattices are going to fall on the spectrum of materials that already exist in the world today. We do this by looking at a material selection chart. It looks really complicated, but it's actually really simple. So on your bottom horizontal axis, you have your density, which just translates to your weight. It tells you how heavy or lightweight your material is. And on the left vertical axis, you have your Young's modulus or stiffness. So it tells you how squishy or stretchy your material is. Essentially how easily your material is going to conform to a given force that's applied to it. So on your top right, you have your metals, because they're really heavy and really strong. And as you move down into the left, you get your polymers and plastics, and you get further down into the bottom left corner, you get foams. Now, the interesting thing about foams is that they have void space similar to our architecting materials, but they still have a relatively lower stiffness. So this is the area that we want to get into at the lab. And so we want to maintain this low density, but getting to a relatively higher stiffness. And you can imagine that this would be really beneficial for applications such as aerospace or any kind of aircraft or things like that. Because your fuel costs, a lot of it goes into how much weight your aircraft is carrying. And we do this by, again, making our lattice structures. And this little star structure that you see here, it is called an octet truss. And this is just a unit cell or basic building block that we repeat into one larger structure to make our full bulk material. And the unique thing about the octet truss is that all of these beams reinforce each other at the connecting points. So whenever you apply a load to it, there's always a beam counteracting your force to make it really difficult to deform the lattice. And in the next video, I'm going to show you just a quick walkthrough of how I use NetFab, another Autodesk software, to create this octet truss. So you start with your empty unit cell, and I need to place nodes or connecting points, these little blue spheres that you see I'm placing in all of the corners and on the edges and in the center faces of the cube. And these are going to serve as, again, the connecting points of the beams. So once all of the nodes are placed, I have to go in and connect the beams one by one with these little orange cylinders that you see here. But right now, these cylinders don't have an actual volume or real volume. They're just visual representations of where the connecting points are going to be. So I need to go in and assign an actual volume and shape a number of sides to the cylinder that are going to comprise these beams. So then once I have my cylinder created, I go in and assign them to all of the beams. So then now I have a full-fledged three-dimensional model. And so I have this little unit cell, and I'm going to tile them or repeat them in the different directions that Julie mentioned earlier. So I repeat it in the X, and now I repeat it over in the Y. And then I stack it up in the Z. And you can notice that as you build this up more and more, it starts to resemble more of your continuous bulk material, but you know that when you zoom in close to inspect each of the elements, you know that you're going to have this really intricate architecture design, which is something that only you can make with 3D printing. Now, architecture isn't something that only happens in the lab. It actually occurs in nature. Is what inspires us to make some of our materials. And one type of architected material or lattice material that occurs in nature that everyone's familiar with is the honeycomb structure. It's a lot of little hexagons that are packed together and that are tiled in 6 different directions. And instances where you can see this show up in our world is with chain link fences, or with pavement, you laying down little bricks to tile them around in 6 different directions. Or for structural purposes, you can place a honeycomb structure between 2 layers of sheet metal, so you get a much lower density part, because again, you can see that you have a lot of void space in there, but you don't have to compromise on your strength because it's still really stiff in the low direction. Now, one really cool instance where architecture plays in nature is in the exoskeleton of shellfish. So this clam that you see at the top, you know that clamshells are really hard and strong, and it's difficult to get into. But when you look closely at the clamshell, you know that it's not just one smooth, homogeneous surface. It's actually more of a brick and mortar structure. There's a lot of little tiles stacked against one another. Now, this mantis shrimp on the bottom, it has a claw that it uses as a hammer. And it has more of a structure similar to the spiral staircase. So as you stack up in the Z direction, the layers rotate between one another. And I can let y'all make your own guesses as to who you think would win if you pit these two against each other. Now, the point that I'm trying to drive home here is that when you add architecture to your material, you can actually enhance the material properties, especially mechanically. Now, keeping this idea in mind, I'm going to hand it off to Chris, who's going to talk to you about some of the architecture materials that we make in our lab at Lawrence Livermore.
Great. So I'm going to tell you a little bit about the architected materials we fabricated at Lawrence Livermore National Lab. So it really brings together everything you've already heard this morning. So the 3D printing process, the advanced material feedstocks, the design of these structures through the CAD models, and now finally actually fabricating these parts and these materials and showing that they have superior properties. For example, what we have here is one of the unit cells, just like Will showed you in his prior explanation. This particular unit cell is that octet truss that he introduced to you a few slides ago. And this was fabricated with the projection microstereolithography system that Eric spoke about and is made from a polymer. In fact, you can take that unit cell and fabricate many thousands of them to create a large-scale lattice, just as you saw Will do in the computer when he designed it. So in this case, we have many thousand polymer unit cells put together in X, Y, and Z space to create this larger lattice, which has really unique and interesting properties. In fact, it has the properties that Will described. It's very high stiffness, very high strength, but if you take a close look at it, you'll notice it's mostly made up of empty space. Therefore, it's lightweight. So we're making high strength, high stiffness, lightweight materials through this concept. This is another example of a similar material. You can see at the bottom being pointed at with the blue arrow. That is also an architected material, and you can see how strong it actually is. That piece of material that we fabricated was only 6 grams in weight, but it's holding up 180 grams, actually 30 times its own weight. And in fact, it could do even better than that. We can continue and make even more complex structures. What you see here is a larger scale structure made with one of our additive manufacturing techniques and then coated with metal, so it's actually made of nickel. And this structure is extremely complex. It's something we might call a hierarchical or even fractal structure. If you zoom in really closely to it, you'll see there are unit cells inside the unit cells, struts made out of unit cells. Why would you do this? This actually gives you even better properties than we had before. We start to approach the theoretical maximum in strength and stiffness for a given weight. In fact, it even starts to exhibit extremely unique properties like ductility. You could actually stretch this a little bit before it breaks, which is very unique for a metal of this nature. And it all comes from the concepts of design, architecture, and enabled by the 3D printing processes. Not only do we work with metals and stiff and strong structures, we also work with soft materials. For example, you see a picture of one here. This is also an architected material. It was printed using direct ink write, which Eric introduced earlier as well. And what you see here are filamentary structures in a woodpile type formation. This particular polymer is soft. It's the kind of material you might find in, say, your sneakers or your football or baseball helmet. We call it a mechanical energy absorbing material. So if you were to shock it or hit it, it would actually compress and absorb the mechanical energy, thereby, in a helmet, thereby protecting your head. And its properties are really derived both from the chemicals and the chemistry of the material and the architectural layout of the material. We could change that architectural layout and it would have different mechanical properties and it would absorb energy in different ways. We can see that in this video. On the far left, you see just a bare piece of metal. In the middle, one of our soft architected materials, and on the right, a different architecture. As the balls drop and bounce back, you can see how much energy is being absorbed based on how high the balls bounce. So clearly, architecture 2 on the far right absorbs the most mechanical energy, and that is derived, again, from the chemistry and the materials and the architecture of the material, which comes from the 3D printing process. So now I'd like to describe to you another really interesting material property and how we can manipulate it as well using additive manufacturing and architected materials. So Melody and Dean are going to explain to you the concept of Poisson's ratio.
So all materials that occur in nature behave in a similar way when it comes to tension. So what happens is that when you pull on a material and you make it longer in one dimension, the other dimension gets smaller. So we're going to show you that one more time. You can see how it gets thinner in the middle. And so what we do is each material behaves in that same manner, but to a different degree. And so what we do is we look at what the change in length is versus the change in this diameter, and we call that the Poisson's ratio.
So what Melody and Dean just showed you is what we call positive Poisson's ratio. It behaves the way you would expect, like a rubber band. It gets skinny when you stretch it. Take a look at this architected material that we printed. As you stretch it, it actually starts to get fat instead. Again, that all comes from the arrangement of the material or the architecture and the 3D printing process. Not only do we work with structural and mechanical materials, but we work on other materials as well. For example, pyrotechnics, or materials that have flames, such as the animation you see here. We're able to print some of these materials called thermites, and we can print them in architected or specially designed arrangements. In this particular animation, you're seeing what we call a channel configuration, where you ignite the material and it propagates very quickly down this channel. So again, it's 3D printed, and there's architecture in the structure. If we take a look at a different structure, if we arrange the material essentially perpendicular to what you just saw, we could then call it hurdles. And it propagates the flame forward in a very different way. So by arranging the material in these different ways, we can actually control how fast it reacts. So we actually did this in the lab, and the videos you're seeing here are of actual thermite material that was ignited in the lab. It takes place very quickly, essentially a bang and a flash in the lab, and it takes about 10 to 20 milliseconds, just a fraction of a second. So the images you're seeing are actually high-speed video, slowed down so you can observe how the flame and the energy moves forward. In this case, you can clearly see the hurdles move more slowly, the channels more quickly. Again, we're controlling the response of the material through the design of the architecture and the 3D printing process. Here is yet another unique material. This is a 3D printed shape memory polymer. So we can print these materials in certain configurations, and then by applying heat or electricity, they actually fold up like origami into pre-programmed structures. Some people refer to this as 4D printing, where the fourth dimension is time. So quite an interesting phenomenon which we can now manipulate through the printing process. And finally, something we're calling multifunctional materials, which I think may be one of the next waves in 3D printing in architected materials. We once again have our soft material, our mechanical energy absorbing material, except one of the layers is printed with metallic nanoparticles, kind of like the particles Eric showed earlier. Those particles are embedded in the soft polymer material, making it electrically conductive. So now as you distort the material, as you strain the material, you actually get an electrical response out of it, as you can see on the multimeter on the left. So not only is the material performing its mechanical job, it's also performing an electrical function as well. Hence, we call it a multifunctional material. Finally, before I turn it back over to Melody, I wanted to point out for those of you interested in the STEM fields, science, technology, engineering, and mathematics, it's also really important to note that you have to communicate your results to your colleagues and others around the world. And we do this many different ways. So communicating your results through conferences, presentations like this one, or publications, as you see up here, several that have been published by our group at Livermore. It's really important to note that communication of what you've done is critical to advancing the field. So with that, I'm going to turn it back over to Melody.
So I hope that you have enjoyed our talk, and I hope that you're feeling inspired to follow us into a life of science and engineering. We have a lot of fun in the lab, as you can see. And so keeping on this whole idea of 3D printing and being inspired to do new and exciting things, we created a 3D printing design challenge that we are going to go over right now. And so what we did is we put a call out to anybody attending this talk to basically design a structure that can handle a very high compressive force. And we're trying to see which one can handle the highest force. So the design's rules were basically centered around our test apparatus, and so they needed to have a hole in the center in order to fit into this test apparatus. It can go up to 1,000 pounds, and we also wanted it to be not fully dense. So this fully dense block we have here, you know, it could easily withstand a high compressive force, but what we were looking for is for students to be creative in how they design these to also be very light, like we saw with our octet truss lattices. And so what we have is we have 3 designs here that we've selected from the group that we thought were very interesting, and we want you to take a look at them and really inspect what those features look like.
Let's do it like that. That way
okay. And I want you to pick which one you think is going to be the strongest for this compressive force. So this we're calling design A, in the middle is design B, and then we have design C. You can see that they each have some kind of unique design features, so take a moment to check them out. And then what I'd like to hear is which one you think is going to get the highest force by a round of applause. Cool, I like the discussion. Very good, collaborative.
This is good.
Awesome. Okay, so we're going to do a quick little vote before we begin crushing some stuff. So who thinks that design A is going to be the strongest? Round of applause. Round of applause. Let's hear it. Awesome. Okay, what about design B here in the middle? All right, that's a popular choice, popular choice. And what about design C?
Okay.
Cool, cool. Awesome, awesome. Okay, let's break some things.
Sure. And let me just take a minute to say that, so as a teacher watching students design some of these blocks, it's just great to see students thinking and coming up with these innovative designs. And so there will be one winning block here today, but I just want to say that engineering isn't about creating something that works on the first shot. It's really about building a prototype, testing it, learning about what worked and what didn't work, and then going and redesigning. And so the students were only allowed really one test, so it's kind of, in a way, it's really not engineering. It's kind of unfair, right? But there will be one winner today. We'll find out. So, so let's start with block A. And let me start off with a 0.
So in this compressive force apparatus, we are going to have a force readout on the front, so we'll be able to see which one can withstand the highest force. So as Dean gets set up, let's take a look at design A, and we're going to notice that it has these crisscross bars. The bars are very thin, and so this could end up distributing the force somewhat evenly throughout the part, but they are pretty thin, so we'll see what happens here.
Okay.
Oh, let's go.
You guys ready?
Break
Okay.
some things. Okay.
I'm going to start pumping this, and this force sensor, there you go, will basically start reading how much force, and what we're looking for is the first sign of failure. We're not trying to crush it down to the smallest, as flat as can be. We're just listening, did it crack? Did it break? And so we're looking for the first sign of failure, okay? So here we go. Okay, that's 36 pounds of force, 68 pounds of force, 104.
Doing pretty good so far.
Yeah. 168. We're over 200.
Oh, there we go. Okay.
224.
224.
So remember that. Here we go.
So you can see things are popping off.
Okay. Oops.
So we can see those thin members started to break there. That was its failure mode.
Okay. And this will come off too. You want to slide that off? Okay. Slide it off the bottom.
Yep.
Okay.
Okay. So next we are going to have design B right here, a very popular choice. So this is a very interesting design because we put it out to the students that it needed to fit within this 6 by 6 by 6 centimeter volume. But this design actually decided to go a little bit shorter. And so that's kind of an interesting perspective. And so I think that could work to its advantage. So it has similarly some crisscrossing beams. It looks to have a higher density of these beams, so the force may be better distributed. But it's also going to distribute that force, I think, a little bit better because it's shorter. So let's see what happens here with design B.
Okay, 128. Over 200.
Okay, doing pretty well.
Over 300. Okay, we're at 400. This is 400 pounds.
Very strong, not budging at all.
500 pounds.
We might max out here.
600 pounds. $700.
There we go. Wow. So I will tell you. Woo! That was pretty awesome. That was pretty awesome. What did we get to?
796.
796.
Wow.
So we almost hit our max, and you can see that was a pretty dramatic failure mode, right? So in the first one, we just started to have things kind of start to snap. But this one, everything just happened all at once, bam. So very cool. So 796 is the number to beat?
796.
Okay, awesome. Here we go, design 3, design C, also very popular choice.
Is that in? There we go.
Look at that. Totally disintegrated. Totally fell apart. Very cool. So, Design C has a somewhat similar configuration to Design B. It has these crisscross lattices throughout it. It looks like some of these X's might be a little bit larger than the last one, and overall that height may be a little bit larger. So we're going to get a chance to compare what happens when you have it nice and short versus a little bit longer and taller.
Okay, here we go. Okay, we're at 100, 200, 300, 400, 500, 600.
Woo! Here we go. I'm stepping back.
Yeah. 700.
Oh, here we go. We're almost there.
Okay, 800.
Yeah.
And I don't know if I'm going to max this out. Am I maxing this out? 900.
Yep, here we go.
This goes to 1,000. If it gets to 1,000, we're going to stop, okay? Because that's as far as it goes. There it is. Okay.
So not only was that the strongest design of this section, but we actually chose some different designs for the first section, and this beat it by far. So I think what's really interesting is to think about how this lattice comes together and how this design was chosen. So it worked really well for its application. If you were to have a different application of maybe you were trying to bend the material, then it might not be the ideal design. So really, really excellent job from all of the students who designed these parts. And I hope you enjoyed that demonstration.